So just like in cooking, where you sometimes run out of one ingredient, that happens in chemical reactions as well. It's very unusual to, say, make pancakes and actually use up all the flour, all the eggs, and all the baking soda in the house, right? That's just not going to happen. You're going to run out of one thing first. And that thing that you run out of is going to limit how many pancakes you can make. So, I feel like I'm missing, am I missing any? No? Yeah, I'm missing a slide. Yeah, okay. What if we had 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder? How many pancakes could we make? Pretend you didn't see that slide I just showed you by accident. Well, how would we figure that out? We could figure out, well, from 3 cups of flour, how many pancakes can we make? Well, let's do that. And some of this we can kind of do in our head, but we're going to write it down anyway. So 3 cups of flour, we can make 5, we'll call them PCs, 5 pancakes for every cup of flour, right? So if we had 3 cups of flour, we could make 15 pancakes. If we had 10 eggs, well, we get 5 pancakes for each how many eggs? 2 eggs. So that's going to give us 25 pancakes, right? If we had enough stuff to use up all the eggs. Half a teaspoon of baking soda powder, 1/2 teaspoon. No. I'm looking at the wrong numbers. 4 teaspoons of baking soda. And 5 pancakes for every half teaspoon. I'm going to write that as 0.5. Way down tiny in the bottom there. 4 divided by 0.5 is 8 times 5 is 40, right? So let's think about this. We're making pancakes. We're making pancakes and we make 5 pancakes and we make 10 pancakes and we make 15 pancakes. At 15 pancakes we run out of flour. Can we make any more pancakes? No, we can't. If we had more flour, we could make up to 25 pancakes with the amount of eggs and baking soda that we have. But we can't because we ran out of flour. The flour limits production of pancakes, right? Once you run out of an ingredient, you have to stop. You can't make pancakes without flour. So we do a calculation like this, and whichever of those ingredients gives us the smallest number, that's how many pancakes we can make. Because when we get to that point, we run out of an ingredient. Any questions? Now we'll go to this slide. So here's our picture. 3 cups of flour would get us a theoretical yield of 15 pancakes. 10 eggs, a theoretical yield of 25 pancakes. And 4 teaspoons of baking soda, a theoretical yield of 40 pancakes. That would be 40 pancakes provided that we had enough of everything else. So in a chemical reaction, we would say that the flour is the limiting reactant. It's the ingredient that limits the product. Okay? Now, suppose we're cooking our pancakes, and we burn 3 of them, and 1 falls on the floor. Could that happen? Sure, it could happen, especially if you have children or animals in your house, right? So we had enough flour to make 15 pancakes, but we only ended up with 11 edible pancakes. That's our actual yield. That's our actual production. We could have made more if everything had gone perfectly, but how often does everything go perfectly? Never, right? Okay, so 11 pancakes is our actual yield. 15 pancakes is the theoretical yield. In theory, we should have been able to make 15 pancakes. Who knew we were going to drop one on the floor, right? And the floor is not that clean, so we got to throw that one away. 3-second rule doesn't apply there. And in a chemical reaction, we have the same idea. Generally, we're not going to have the exact amounts of each reactant. Just like in your kitchen, you don't have the exact ingredients to make a certain number of batches of pancakes. There's extra of stuff. There's always going to be one thing that runs out. So we've got that theoretical yield and that actual yield, and the way we find convenient to express that is as a percent yield. So percent yield is the percentage of the theoretical yield that was actually obtained. It's the part, the amount that we actually made, divided by the whole, the amount we could have made, times 100. So if everything went perfectly, our percent yield would be 100%. We didn't screw up, nothing bad happened, the chandelier didn't break, and that happened with a birthday cake once. The light fixture just fell off the ceiling. No earthquake, this was in Iowa. No earthquake, it just fell and shattered, and there's glass everywhere. And it's like, well, that birthday cake is toast. We're frosting the cake. Glass in the frosting, not good. Who knew that could happen? Stuff happens. If nothing bad happens, you could get 100% yield. But usually it's going to be less. So in this situation, we made 11 pancakes out of a 15 possible, and so our yield was 73%. The actual yield that you get in a chemical reaction is always determined experimentally. Just like the actual yield making pancakes. You can't predict how many pancakes you're going to screw up, right? And it might not even be the same. It probably won't be the same from time to time. So the actual yield comes from an experiment. So there's no calculating that. The actual yield is almost always less than 100%. And this can happen for many reasons. Some reactions do not go to completion. I guess that would be like, you're letting the 9-year-old make pancakes, and she got tired of making them. So she only made 12 of them and didn't cook the rest of them. It didn't go all the way to completion. And some chemical reactions are like that. Or perhaps, the reaction was complete, but in the process of recovering it, you lost some. I think you've seen in lab how that could very easily happen, right? You dropped some on the floor or something. And so you actually made more, but because you flubbed up a little bit, what you end up with is less. Occasionally, we'll just stay there for a minute. Occasionally, the percent yield is greater than 100%. How could that happen? Well, that usually means that there's something wrong, right? What could go wrong? Well, a lot of times when we make a solid and we filter it, it's wet. And if we weigh it before it's completely dry, then we get the mass of the water included in the mass of our product. And that makes the product weigh more, or appear to weigh more than it actually does. And so that could get you over 100% yield. So if it's wet, it could be greater than 100%. You could also have some sort of a contaminant in there, which could have been added knowingly or unknowingly. That reminds me of an experiment I was doing in a quantitative analysis lab, and it was this long procedure, and we were graded entirely on our percent yield. We had been ashing this thing where we burn stuff off, and one of my fellow students, he's working very diligently. A fly flies over, is killed by the heat, falls into the crucible and burns up. And we're like, what? Did that just happen? That really happened. Now, what's the poor guy supposed to do? He's screwed, right? Because this was like a 3-hour experiment, and we're at the very, very end. You can't just do it over again. So then you think, okay, we need to correct for this somehow. If only we knew the mass of an ashed housefly. So he went around and caught 10 houseflies, killed them, ashed them, measured their mass divided by 10, and subtracted the average mass of an ashed housefly from his product. You know, that's the best we could do. Well, it was a very old building with windows that opened and no screens. And so, yeah, catching 10 flies was not that hard. We occasionally had, streams of wasps coming in. Those are the good old days. Anyway, there are lots of different things that can happen. If the product percent yield is over 100%, there's a problem of some kind. But when you're doing calculations, if you get over 100%, by all means, check your work, but don't assume that you've done something wrong, because they may give you a homework problem where it's like 102% or something. If you get 5,000%, then you've definitely screwed something up. So, to summarize all of this stuff, when we talk about a limiting reactant, or sometimes we call it a limiting reagent, reagent is a fancy word for the chemicals that we use in an experiment. The limiting reactant is the one that is completely consumed. It gets used up. And that's the one that limits how much product you can make. That's why it's called limiting. It's the ingredient, the reactant, that limits how much stuff you can make. The theoretical yield is calculated using stoichiometry, like we just learned how to do today. And that's based on the amount of the limiting reactant. We don't care about the amounts of the others. Like with the pancake idea, we had a certain number of cups of flour that limited how many pancakes we could make. The number of eggs, the number of teaspoons of baking soda doesn't matter because there was extra. We're concerned with the limiting reactant. The actual yield is the yield that you actually get. And that's not something that you're going to calculate. If you're doing a percent yield problem, they will tell you the actual yield. You calculate the theoretical yield, and then calculating the percent yield is the actual over the theoretical times 100. So let's look at a chemical example. What are the limiting reactant and the theoretical yield for this reaction between titanium and chlorine if you start with 1.8 moles of titanium and 3.2 moles of chlorine? So what we're going to do is we're going to use stoichiometry to find the amount of each product, the amount of product that can be made from each reactant. So here what we're doing, because we have two reactants and we're trying to figure out which one's going to limit, just like with the pancakes, we're going to do more than one calculation. We're going to see, okay, we've got 1.8 moles of titanium. If all of that gets used up, how much product can we make? And we'll see what that is. And then we have 3.2 moles of the chlorine. How much of that? How much product would we get from that? And this first example, we're using moles so that it's a little simpler. So 1.8 moles of titanium, and that's going to be multiplied by 1 mole of titanium chloride, it's titanium 4 chloride, divided by 1 mole of titanium. Because when we look at this equation, for every 1 mole of titanium, we get 1 mole of product. So if we start with 1.8 moles of titanium, we're going to end up with 1.8 moles of product. And this is really not, the slide is not set up for this. I'm going to go down here where there's a little bit of space to do the other one. 3.2 moles of chlorine. Well, how many moles of titanium 4 chloride? Well, we'll get 1 mole of titanium 4 chloride for every 2 moles of chlorine. Two moles of chlorine get us 1 mole of product. 2 moles of chlorine for 1 mole of product. So that should be, what, 1.6? So I take each starting amount of reactant and I do a separate calculation and find out how much product. Then I'm going to ask myself which one is smaller, 1.8 or 1.6. 1.6 is smaller. Because as this reaction goes along and you're making 1 gram and 1.2 grams and 1.4 grams, when you get, moles, when you get to 1.6 moles, it stops because you ran out of chlorine. There's more titanium, but you can't react it because you ran out of chlorine. Just like with the pancakes, you run out of flour, you got to stop. So this is our theoretical yield. And what is the limiting reactant? It's the one that gave us that. So here's the smallest. That's our theoretical yield. Just go back to the beginning of this, and that's our limiting reactant. So that's limiting reactant, LR. So you will be doing some calculations like this in a lab. And occasionally students will they'll do all the calculations, they'll write this all out, and they'll write that all out, and then they just leave it. You have to tell me what the answer is. And on a lab report, I will accept circling or putting a box around the smaller one. It'd be nice if you at least put TY for theoretical yield or something, and then circle or box or somehow indicate that this is the limiting reactant. I need to see that you know what to do with that information. Any questions?
The actual yield is only when you do a lab?
The actual yield comes from an experiment. So in this example, we have no experimental data, and so we have no way of knowing an actual yield.
For like a test, question on test, will they give you an actual yield? Like
If they want you to calculate the percent yield, if there's anything where you need an actual yield, they would have to give it to you.
Okay.
They'd have to give it to you. So if they hand you a number, and we'll see some examples like that. Oh, well, that's why there wasn't enough space, because I was supposed to write all that over here. My bad. Let's do another one. Sodium and fluorine reacting to form sodium fluoride. If you begin with 4.8 moles of sodium and 2.6 moles of fluorine, what's the limiting reactant and theoretical yield of sodium fluoride in moles? Well, let's use the equation to organize these numbers. 4.8 moles of sodium. So I'm going to write that under sodium. 4.8 moles of that and 2.6 moles of fluorine. And the question is, how many moles of sodium fluoride? And what's the limiting reactant? So we're given 2 amounts. We're going to do 2 calculations. So 4.8 moles of sodium will make how many moles of product? Well, so we've got moles of sodium fluoride and moles of sodium. We get our units in there. We look to the equation. 2 moles of sodium give 2 moles of sodium fluoride. So we're going to end up with the same number of moles of sodium fluoride as we started with for sodium. Then I'm going to take the other number, 2.6 moles of fluorine. And I'm going to do a similar calculation. I'm going to multiply by moles of product and divide by moles of reactant. And I look at the equation to get the numbers. 1 mole of fluorine for 2 moles. 2 moles of sodium fluoride from every 1 mole of fluorine. So I end up with 2 answers. But I can only have one answer. It's the smaller one. Do not add them together. Don't do anything crazy like that. Just pick the smallest one. That's the easy part, right? Just pick the smallest one. Well, 4.8 is smaller. So this is our theoretical yield. If everything goes well, that's how much we could make in moles. And then this is there's 2 questions. What's the theoretical yield and what's the limiting reactant? The limiting reactant is sodium. So sodium is the limiting reactant. And for homework on this with Mastering Chemistry, be sure they tell you this is how we want the answer, and so be sure to put it in there the way they want it. Any questions? So this whole idea of percent yield and limiting reactants is very important in industrial applications and manufacturing, because usually the ingredients do not have the same cost. And you think about like if you're making blueberry pancakes, okay, the blueberries are going to be expensive, right? So you're going to buy just enough blueberries and make sure you have plenty of everything else, because you don't want the blueberries to be left over. So typically what they do in industry is the more costly reactant is going to be intentionally made the limiting reactant. Or sometimes there's a reactant that's difficult to remove from the product mixture. Because if you're, it's not like in your kitchen making pancakes where those other ingredients stay there. In chemistry, when you're doing this reaction, they all get thrown in together. And product is made, but then the leftover reactants are still there. And some of those may be harder to remove than others. So if you have one that's really hard to get away from the product, then you might make that one be the limiting reactant, so you don't have to deal with that at the end. Now, in the lab, we do this with grams and not with moles. So to find limiting reactants and theoretical yields from masses, we have to add 2 steps. So now we're going to combine the idea of the limiting reactant with that full-blown grams to moles to grams calculations that we did earlier. So if we had a situation like this, reacting sodium with chlorine to form sodium chloride, if we're given that it starts with 53.2 grams of sodium and 65.8 grams of chlorine, find the limiting reactant and the theoretical yield. So this is kind of a picture of how we go about doing that. We've got 2 quantities here, so we're going to do 2 calculations. So you're going to get a lot of practice at these stoichiometric calculations. 53.2 grams of sodium. We're going to take grams of sodium to moles of sodium sodium chloride to grams of sodium chloride. And these are the conversion factors. The first is the molar mass of sodium. This is the mole ratio from the equation, 2 to 2. And you're going to do each of these calculations, and then the smallest amount is your product, and the one that gives you the smallest amount is the one that is the limiting reactant. So this is the same as what we were doing with moles, but now we're converting from grams to moles at the beginning and converting from moles to grams at the end. We're just adding a little bit to each end. So all written out, it would look like this. So here we've got all of our units canceling out beautifully. Grams to moles to moles to grams. This one gives 135 grams. Here's the chlorine. Grams to moles to moles to grams gives 108. We look at these two numbers, 108 is smaller. This is the amount of product that can be made. Because when you get to 108 grams, you run out of one of your ingredients. You run out of the chlorine. The chlorine is the limiting reactant. So the pattern here is you've got two quantities. You calculate amount of product separately from each. Identify the smaller. That's the amount you can make. Look back and see which reactant gave you the smaller. That's your limiting reactant. Yeah, there's something missing in here. So this is the same example. They need to tell you the actual yield. So that's included in the given. So given the 53 grams of sodium and the 65 grams of chlorine, and being told that the actual yield is 86.4 grams, find the percent yield. Well, the percent yield is the actual yield divided by the theoretical yield. The theoretical yield is what you've calculated using the long equation. That's 108 grams. We calculated that on the previous slide. This is what we're given, 86.4. We're told this is the actual yield. In lab, this is the number that you measure. You weigh your product, that's how much you got. That's actual yield. So you do the math here and you end up with 80%. So the percent yield is 80%. So let's do an example. Ammonia can be synthesized by the reaction between hydrogen and nitrogen, given here. What maximum amount of ammonia in grams can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen? Always read all the way through the question. Usually if they give you two masses, it's going to be a limiting reactant problem. So I'm going to take these numbers and put them in the equation here. Nitrogen, it says 25.2 grams. And for the hydrogen, it's 8.42 grams. So I'm going to do two calculations. So first I'll do the hydrogen. Doesn't matter which one you do first. 8.42 grams of hydrogen. I need to convert that to moles of hydrogen, grams to moles of product, moles of ammonia, to grams of ammonia. There are other ways to solve these problems, but I think this is by far the most straightforward method. So then I get my units in here so that they're going to cancel out the way I need them to. So moles of ammonia, cancel, moles of hydrogen, cancel, grams of hydrogen, cancel. So we have to figure out the molar mass of hydrogen. It's 2 times 1.008, so 2.016. And the ratio of ammonia to hydrogen is 2 to 3. 2 moles of ammonia for every 3 moles of hydrogen. And then ammonia, let's see, 03? Is that right? It's 14, I know it's 17 something. 14.01 for the nitrogen, plus 3 times 1.008 for the hydrogen. Yeah, 17.034. So we've got 8.42 divided by 2.016 times 2 divided by 3 times 17.034. And that number will have 3 significant figures because of the 8.42 having 3. So that's 47.4 grams of ammonia. Now we're going to do a very similar calculation with the nitrogen. 25.2 grams of nitrogen. We're going to convert to moles of nitrogen. Grams of nitrogen will be on the bottom. Sometimes my hand just writes things and I don't know why. Moles of ammonia on top. And we need moles of nitrogen down here. And then at the end, this last term is going to be the same for both of them. Grams of ammonia per mole. So I don't need to calculate that number again because this is the same. And those units are going to cancel. And in the middle here, it's 2 moles of ammonia for every 1 mole of nitrogen. The moles of nitrogen are going to cancel. The molar mass of nitrogen is 2 times 14.01, or 28.02. 25.2 divided by 28.02 times 2 times 17.034 equals. .6 grams of ammonia. If I have enough nitrogen, and use up all the hydrogen, I can make 47.4 grams. If I have enough hydrogen and use up all the nitrogen, I can make 30.6 grams. Which is the one that I can actually make? It's the 30.6. It's the smaller one. Because when I do that, I run out of nitrogen. Nitrogen is the limiting reactant. The question says what maximum amount of ammonia can be synthesized. The answer is 30.6. Questions? Okay, here's another one. This reaction is used to obtain iron from iron ore. And you can imagine that someone in the mining industry would be interested in the percent yield of this process, right? So the reaction of 185 grams of iron 3 oxide with 95.3 grams of carbon monoxide produces 87.4 grams of iron. Find the limiting reactant, the theoretical yield, and the percent yield. Like, oh my goodness, there's 3 numbers in there. It's okay. So 185 grams, 185 of that, and 95.3 of the carbon monoxide. And then it says 87.4 grams. And you're like, oh, wait a minute. They gave us the mass of product? Why are they asking us to calculate the theoretical yield? Well, what is this guy right here? That's the actual yield. They're saying it produced 87.4 grams. They are giving you the actual yield. They're saying we reacted this, and this is what we got. How much should we have gotten if everything worked perfectly? So this is the actual yield. We're going to need that number for the percent yield. But first we have to do our calculations. Okay, so let's start with the iron oxide. 185 grams Fe2O3. And grams to moles to moles to grams, right? So grams of that to moles of that, Fe2O3. To moles of what we're interested in, which is iron, to grams of iron. There's an E there. Moles of Fe, so those guys cancel. Moles of Fe2O3, those guys cancel. And grams of Fe2O3. So those guys cancel. I'm going to do my molar mass calculation way up at the top. Iron is 55.85. 2 times 55, come on, 55.85, plus 3 times 16. 2 times 55.85 plus 3 times 16 equals 159.7. That is the mass of 1 mole of Fe2O3. 1 mole is 159.7. In the middle, these numbers come from the equation. There's a 2 in front of Fe, so I'm going to put a 2 in front of moles of Fe. Fe2O3 has nothing in front of it. It's an implied 1. And then grams of iron, well, that's nice because that's an element, and we just look that up on the periodic table. So 185 divided by 159.7 times 2 times 55.85 equals. With 3 sig figs, that comes out to 129 grams of iron. So if the iron oxide is the limiting reactant, that's how much product we're going to make. If the carbon monoxide is limiting, then we have to figure out what that is. So 95.3 grams of carbon monoxide. Grams to moles to grams. It's the same pattern every time. Grams to moles to moles to grams. I want moles of Fe to cancel out. I want moles of CO to cancel out. I want grams of CO to cancel out. I know this last one is going to be the same, so that's kind of nice. The middle one, moles of iron, comes from the balanced equation. There's a 2 in front of Fe, and there's a 3 in front of the carbon monoxide. And then I need the molar mass of carbon monoxide, which would be carbon plus oxygen, which should be 28.01. So I get 95.3 divided by 28.01 times 2 divided by 3 times 55.85 equals This one, rounded to 3 sig figs, comes out to 127 grams of iron. What's my theoretical yield? 127. Did you guys come up with the same numbers? Okay. Because I do screw up a lot. So there's our theoretical yield. That's one of the questions. Find the theoretical yield. Boom, there it is. Limiting reactant. Wherever that theoretical yield was, just look back what reactant gave you that. It's the carbon monoxide. That's the limiting reactant. And what is the percent yield? The percent yield is we're going to take the actual, which was given to us, 87.4 grams. And we're going to divide that by the theoretical yield that we just calculated, the 127 grams. Notice that those grams cancel out. So there's no grams in our percent yield. 87.4 divided by 127 equals times 100. And that should have 3 sig figs as well, 68.8%. That's our percent yield. Any questions?